Thank you for the presentation. So we will stay on topic with the previous presentation of Raul. We're just going to switch from SLM or laser powder bed fusion to DED. And so I'm not going to spend much time, I think, in the theoretical introduction. We're all very, I assume, quite familiar. So we have usually tensile compression tests to characterize a material statically. Then fatigue tests are usually try to characterize the initiation stage of failure, while obviously linear elastic fracture mechanics specimens, like the CT specimen, which we will study today, are concerned with just the propagation and critical failure stages. So the most valuable output in these type of tests is the Paris curve or Paris-Serre curve, initiation, regime 1, then a stable propagation, and then critical failure. So yeah, instead of laser powder melting fusion or laser powder bed fusion, the specimens were manufactured via directed energy deposition. Very similar procedure. The only difference is that basically this robotic head in which the nozzle is mounted to and the energy source, they're all, let's say, moving together, and powder is being coaxially ejected, and basically we're building a layer by layer part in this fashion. And so in this work, we were particularly concerned with dendrites. Dendrites are not really so novel. They also appear in casting, welding, any, let's say, process very out of equilibrium. But we are particularly concerned with how a crack interacts with these pre-existing dendrites. So here in this image, we already see quite a bit of different morphologies, and they arrive due to these two variables, let's say. So the temperature gradient ahead of the cooling front and the growth rate, which is, yeah, or basically how fast everything is cooling. The product of these variables defines the dimension of the dendrites, while the ratio between them defines its nature. And so basically in directed energy deposition, maybe even more so than in SLM, the product is highly textured, and we are concerned with basically how the crack will interact, let's say, transversing longitudinally, particularly in the columnary dendrites, versus having to break through them by propagating transversely. And to achieve this, basically, we have these two geometries, LS, SL. LS is analogous to this vertical crack here, while the SL is this horizontal crack. We will test the CT specimens in its aged condition and as built. As built just in terms of metallurgy. So obviously the specimens have to be manufactured through EDM. So I'm not going to lose much time. Raul just presented this very well, what is maraging, the chemical composition and applications. And so again, I emphasize these two types of specimens. Okay, so the LS specimens, the crack will have to propagate parallel to the building direction. SL, it's perpendicular, these two directions. And this was the heating or the heat treatment subjected to specimens that eventually were heat treated. This was the CT testing setup, so fairly linear, Hummel machine. Tests were approximately at 70 hertz. We had a clip gauge to measure the crack length via compliance method, but we also checked the results with optical measurements. In terms of results, so very important distinction before we even talk about the Paris curve is the morphology of the crack in terms of macroscopic dimensions. So in fact, this specimen here, SLA, despite me showing these results, this would be considered invalid if we followed ACM E647. I am just showing it so we have a comparison. So here, at first glance, one can assume, all right, the crack probably is trying to accompany the dendrites that are perpendicular to the main crack direction or propagation direction. And so that's probably the reason why this crack deflected so much. And even the second specimen, which was tested under decreasing delta K values, it still suffered a very significant deflection. In terms of, let's say, aged and LS condition, I would say the curves are very similar in general terms. Comparing to the literature and basically plotting the results as a simplified Nesbro model, we can see that aging had this homogenizing effect. So if we go back to the first slide, there is considerable difference between SL and LS tests. After aging, basically all of the results kind of collapse together and are basically in line with the literature on DED crack propagation tests. All right, so the main focus of this work, let's try to quantify the actual influence of all of these dendritic structures on propagation. And so we basically measured the angle between the dendrites and the main propagation direction. I'm just going to skip for now for the main results. So we could see in some cases, like some, let's say, drops in propagation once the crack had to transverse from one regime to the other, or rather from one specific pocket of dendrites to the other. And to better visualize this, we made these plots. So here we are trying to analyze how the crack propagated versus what the model would say it would propagate at that crack length. So positive values mean the crack actually propagated slower than what we would predict. Negative values would be obviously the opposite. And so to help interpret what we are seeing, we see that in as-built conditions, there is quite a large scatter between these values, while aging basically means that even as delta K increases, most of the results are kind of like oscillating around 0. So this is for SL, meaning when the crack had to travel perpendicularly, when the crack propagated in parallel to the colonary dendritic directions, these differences are also not, let's say, so exacerbated. To finalize these little experiments that we made, we also had this idea, what if we try to characterize the tortuosity of a crack? Tortuosity, following this definition, but here we try to simplify, so a straight line would have 0 or null tortuosity. A circle would have as well, because there's no gradient in terms of curvature. Smooth line, obviously positive. A very squiggly line, a very large tortuosity. And so we measure this in terms of macroscopic dimensions to all of the cracks. And we see that despite this having some, let's say, interesting insight, it has very weak correlations mostly with the crack length. Let's say the most valuable insight tortuosity provided us was, if tortuosity, which are these two plots here in two different cracks, if tortuosity changes considerably in like a segment, then we also saw that the crack growth rate also changed significantly, either increased or decreased as tortuosity increased or decreased. So in terms of main conclusions, yeah, as expected, so aging had this homogenizing aspect in terms of either SL or LS specimens behaved quite similarly, even though their as-built counterparts did not. Though the dendritic influence decreases as delta K increases, as there is more energy given to the system to grow the crack. So let's say one future outlook will be using these both of these insights, tortuosity and dendritic influence, to try to, let's say, come up with a geometric parameter that better fits the standard Paris-Erdogan law. So I'd like to thank these projects for my stay here, and yeah, open to questions.